All right, so this presentation is done by Julia Lopez, Nathaniel Rudman, Matthew Hibbert, and Patrick O'Sullivan. Our team name is the Squids, and this is our understanding of turbo machines. Now, the method we have used for this presentation is we have created a little game where you can explore all the types of turbo machines. All the models in this were handmade. Most of them were made in Blender here. Here you can see the simple animation for the centrifugal pump playing backwards. And then here you have your overall playing field. You hit the little play button, and then you're this ball. You can roll around, you can cruise, you can see what's up, you can pause, kind of float around like a little camera. And this is how we chose to present our presentation on turbo machines.
So we're going to start off with just like a little introduction of turbo machines with a small PowerPoint written up by all four of us. So turbo machines consist of multiple blades attached to a rotor, and these blades are mounted on the rotor to exchange fluid energy and mechanical energy. The fluid can be a liquid, a vapor, or a gas depending on the application of the turbo machine. The fluid dynamics and compressibility effects would also differ depending on the fluid, but the basic operating principles would remain the same. There are two types of turbo machines: pumps and turbines. Pumps add energy to the fluid, and they do work on the fluid, thus increasing the pressure of the fluid. Blades on the rotor would force the fluid to move, which then exerts a shaft torque. Some examples of pumps include simple window fans, propellers on ships or airplanes, also compressors in automobile turbochargers. So to the right, there's a picture of propellers on a cruise ship. Turbines extract energy from the fluid, therefore the fluid does work on them, and in order to produce shaft power, a moving fluid would have to force rotation on the blades attached to the rotor. Some examples of turbines include gas turbine engines on aircrafts, steam turbines used to drive generators, and high-speed air turbines used to power dentist drills, which is shown on the right as well. Then there's the flow within a turbine, which can be classified as axial, radial, or mixed flow. Axial flow would be the flow in line with the shaft. With axial flow, there's a smaller pressure gradient and the fluid moves at a higher volume. With radial flow, the flow is perpendicular to the shaft, and there is a large pressure gradient, which causes the fluid to move out at a lower volume. Mixed flow is just a combination between the two.
All right, so Nathaniel's back in the house, and what I'm going to do is I'm going to take you through these four pumps on the left. On the left, we have the centrifugal pump, and how that works is you basically have fluids coming in here, and it gets spread out through this fan, and it gets shot up through this tube. That operates best at high heads and low flow rates. Here is the same pump, it's just a bit more, it has a little opening in it so you can see better what's going on. Next up, we have the actual flow pump, and how this works is it basically has a propeller at the front, and what that's doing is that's pulling the liquid back, and then behind that, you tend to have fixed stator blades, and those just kind of help with the flow. And then it's important to note that in all these models, these little tubes coming back, those are the drive shafts. And this pump operates best at low heads and high flow rates.
All right, hello guys, this is Matthew speaking. I will be talking to you guys about fans and turbines. All right. Okay, so fans, or for fans, the fluid medium that it's moving is typically air, gas, or vapor. They typically have pretty low rotational speeds, about like a few hundred to a few thousand RPM. But even with the low rotation speed, they're capable of moving high volumes of air. Like a standard ceiling fan on like a high setting is capable of moving roughly 5,800 cubic feet of air per minute, which is quite a lot, all things considered. Fans increase fluid's velocity, but they have very minimal effect on its actual pressure and density. So when performing calculations with it, the fluid is often considered incompressible. With the low pressure change with interacting with the fan, most fans utilize lighter weight materials, since it's easier to spin a lightweight material and it won't be damaged due to the small pressure gradient that occurs within the system. Some industrial applications of fans include high temperature circulation of air, saturated air exhaustion, and airborne dust extraction. Okay, on to Turbines, unlike fans, turbines' purposes are to extract energy from the flowing fluid, and its mediums include both air, vapor, gas, and liquids. But liquid turbines are specifically referred to as hydraulic turbines, while and vapor turbines are called gas and vapor turbines, respectively. There are two separate categories for turbines: impulse turbines and reaction turbines. Impulse turbines specifically use kinetic energy from the spinning turbine blade to generate electricity. Impulse turbine is these blades on the left right here. The blades are referred to as buckets, and as the fluid flows and hits the buckets, it will spin the turbine blades, and the fluid, when it comes in contact with the blades, has a relatively constant pressure and velocity, and the blade designs are pretty symmetrical. And on the other hand, you have reaction turbines. This is a reaction turbine, and then this is an open section so you can see what's going on. Reaction turbines utilize the pressure gradient as the fluid as it expands through the blades as the means to produce energy. The turbines have alternating asymmetrical blades, so that as the fluid expands as it passes through, it will spin the turbine blades, leading to an overall decrease in pressure at the outlet of the turbine and an increase in the velocity of the fluid.
Hey guys, it's Patrick, and I'm going to be continuing by talking about a little bit of the mathematics behind turbo machines. So to start off, the equation V is equal to W plus U is really important, where V is equal to the absolute fluid velocity, W is equal to the relative velocity with respect to the moving fan blades, and U is equal to the blade speed, which is equal to omega R, where omega is the angular velocity and R is the radial distance. In a lot of these, in this chapter, we assume that a fluid is perfectly guided by the plane. This means that fluid enters and leaves the turbo machine at the same distance from the axis of rotation. The Euler turbo machine equation is really important. It is represented below, and in it we have T, or the torque shaft, equaling where a negative is equal to inflow, so the mass in times the radius r1 times the velocity theta plus the mass flow 2 times the radius 2 times the velocity out. But this velocity is, of course, angular velocity. So I'd also like to talk about some performance characteristics that we use to describe pumps. So we have efficiency is equal to power gained by the fluid divided by shaft power driving the pump. This is very similar to what we see in thermodynamics in terms of efficiency of a turbine, but a little more representative of our class. And below we have a graph depicting efficiency as a function of flow rate and also brake horsepower and head. It is obvious that at a certain point, efficiency starts to decrease after a certain flow rate, so we have to maximize that. Here we have scaling laws. We would use these scaling laws if we were modeling a pump in the laboratory and we wanted to estimate the characteristics of a larger pump under the same family of pumps with different, say, starting conditions or operational conditions. And they can be represented below, where Q is equal to flow rate, omega is equal to angular velocity, D is the diameter, W dot is the power workshaft, rho is the density, and yeah. So here are our sources. Thank you for watching our video. Hope you enjoyed it.